Hello everyone, I welcome you all in my next lecture of heat and mass transfer subject. So today we will having lecture 7 of this heat and mass transfer. So before we start this class, I would like to revise the previous topics which we had, which we discussed in our previous classes. So there we had discussions on heat, on temperature, on units of heat, units of temperature, and then we discussed about the modes of heat and modes of heat transfer. So in modes of heat transfer, yes, we have seen there are three modes of heat transfer: conduction, convection, and radiation. So conduction, it occurs through solid medium. Convection, it occurs through liquid or gaseous medium. And radiation, there is no medium is required. So these three we discussed. And in conduction we have seen the Fourier's law of heat conduction. The formula of conduction is Q equals to minus K into A dt by dx. And in convection we have seen the formula of Newton's law of cooling is, yes, tell me, H into A into Ts minus Tf. And the last one, radiation, the formula of Stephen Boltzmann law is Q equals to sigma A epsilon into T1 power 4 minus T2 power 4. So this we discussed about modes of heat transfer. Then we started from conduction. So in conductions we have seen general heat conduction equation for slab Cartesian geometry, then general heat conduction equation for cylindrical geometry, then general heat conduction equation for spherical geometry. Then we have seen the formula of heat transfer for slab body is one dimensional without heat generation and steady state. The formula of heat transfer in slab is Q equals to K into A T1 minus T2 by L. And for cylinder, the formula is 2 pi K into L T1 minus T2 by ln of R2 by R1. And the last one, for spherical body, Q equals to 4 pi K R1 into R2 into T1 minus T2 by R2 minus R1. So today we'll be starting our next class on the heat transfer. Now in the previous classes we discussed about the single slab or single cylinder or single spherical product, but now we'll be discussing on composite geometry, means we'll be adding the slab with one more slab or with two more slabs. So with n number of slabs if we add, then what is the amount of heat transfer, that we'll see. So here you can see here heat flow through composite geometry, that means slab or wall. So this is a first body you have been taken. So first you just look at this diagram. First you try to visualize this picture in your mind. So in this picture you can see how many slabs you have taken. Yes, you have taken three numbers of slabs. So you see the first slab has thermal conductivity of K1. The second slab has thermal conductivity K2. And the third slab, the thermal conductivity has K3. Now you can see the thickness of the slabs also. The thickness of the first slab is L1, the thickness of the second slab is L2, and the thickness of the third slab is L3. Now you have assumed that the area of the all the slabs are same. It is A. So you see this is the slab, and the thickness of this slab is L1. Next another one slab, this is the slab, and thickness of second slab is L2. So heat is transferred from the side. So from the side or from the wall, if heat is transferred, then you see the temperature is Ti. Now you have taken another one condition here, that air is present at the inside of the wall, at the outside of the wall also air is present. Now you tell me how the heat will be transferred from one side to another side. So first you try to analyze it. So if I say that a heat will be transferred from air to the first slab, yes, is it correct? Yes, because if air is present means through the air to wall heat will be transferred. Next, in the next steps, the heat will be transferred from first wall to the second wall. Means through the first wall, heat will be transferred. In the next case, heat will be transferred through the second wall, and in the next case, heat will be transferred through the third slab. Now after continuing it, now where the heat will go? Now you see, outside of the wall also air is present. So heat will be transferred from third wall to the environment or the outside air. So you can see here, three walls are there. Inside there is air and outside there is air. So inside air temperature I have taken or I have assumed is Ti. Outside air temperature is T0. At the inside of the first wall temperature is T1. At the outside of the first wall temperature is T2, which is same as the inside of the second wall temperature. So that is T2. And same way, at the outside of the second wall and the inside of the third wall, that is the interface, the temperature will be, yes, it will be same, and the value is T3. And at the outside of the third wall, the temperature is T4, and at the ambient the temperature is T0. Now I have taken another one assumption that Ti is more than T1, is more than T2, is more than T3, is more than T4, is more than T0. Now you tell me from which to which directions heat will be flowed. Heat will flow from Ti to T0 direction or T0 to Ti direction. Now I told you already that in generalized case, always the flow occurs from high to low gradient. So here also heat will flow from Ti to T0. Yes, from heat will flow from inside to outside. Now I will divide this heat into number of steps. So first the heat flows from inside to from inside air to the first wall. So means from Ti to T1. Now the question comes, what is the mode of heat transfer? Now you see what is the medium of this heat transfer? Yes, the medium of the heat transfer is air. So tell me, air is solid or liquid or gas? Yes, it's a gaseous body. That means there convection mode of heat transfer will occur. So tell me now, in convection mode of heat transfer, the formula which you will follow: Fourier's law, Newton's law of cooling, or Stephen-Boltzmann law? Yes, you follow for Newton's law of cooling. So I remember the formula, so I can recall it. Q equals to H into A into delta T. Now here in this case, H how much is taken? Hi means in convective heat transfer coefficient inside, multiply with A. A means area, multiply with Ti minus T1. That means temperature difference between inside air to the first wall. So I can write the value of Ti minus T1 equals to T1 divided by Hi into A. Now again if we continue this process, so you see from the diagram, now the heat is at end of the first wall. So now if we continue the energy, the heat will carry, or heat will be carried out from the first wall to the second wall. That means through the first wall heat will be transferred. So here you see, through first wall heat is transferred from T1 to T2. Now you tell me, what is the mode of heat transfer? So it is been carried out, it has been carried through solid body. That means there is the mode is conduction. So in conductions we have to follow the Fourier's law. Now you tell me, in conduction mode, this is my slab or cylinder or sphere. Yes, it is slab. So for slab already we calculated the value of heat transfer, and the formula is Q equals to K into A into T1 minus T2 by L. So now as per the given assumptions, we can write the equations Q2 equals to K1 into A into T1 minus T2 by L1. So T1 minus T2 comes Q2 into L1 divided by K1 into A. Now if we continue the energy, if we continue to charge the energy to the wall, then through second wall also heat will be transferred from T2 to T3. Now you tell me, What is the mode of heat transfer? Yes, it is conduction mode. So in conduction mode, the heat will be transferred, and I know the Fourier's law of heat conduction. Now you tell me, this is slab, cylinder or sphere? Yes, it is slab. So for slab, the formula is Q equals to K into A T1 minus T2 by L. Now as per the assumptions or nomenclatures given here, I can write this Q3 equals to K2 into A T2 minus T3 by L2. So T2 minus T3 equals to, finally we get here Q3 into L2 by K2 into A. Now same way through third wall also heat is transferred. So from T3 to T4, so heat transfer is conduction mode. So Q4 will be how much? K3 into A, T3 minus T4 by L3. So T3 minus T4 will become Q4 into L3 by K3 into A. Now you see the heat is at end of the third wall. So now from here at the end of the third wall, will the heat be transferred? Yes, it will be transferred. How? From the third wall, means from the end of the third wall to the ambient air. Now in this case, what is the mode of heat transfer? It will be convection, because this is gaseous, is a medium. So in convection mode, we know the formula Newton's law of cooling. So as per Newton's law of cooling, we can write the formula Q equals to H into A into delta T. So as per the nomenclatures, I can write the formula Q5 equals to H naught into A into T4 minus T naught. So what is this H naught? H naught is the convective heat transfer coefficient outside, okay, outside air. So A is the area and T4 minus T naught is the temperature difference between the wall and air. So we can write T4 minus T naught in equals to Q5 by H naught A. So now what you do? You just add this, all the equations. Now the questions will come, why you are adding this? So you see, the heat is transferred from the first wall to the, means from the inside to the outside. So this heat is transferred from inside to outside. So what is the main, or what is the total potential difference? Why this heat is transferred from inside to outside? Because of the total potential. How much is the total potential? It's not Ti minus T1 or it's not T1 minus T2. Total potential is Ti minus T naught. So to get this value, we have to sum up all these equations. So if I add the left hand side, it looks like Ti minus T1 plus T1 minus T2 plus T2 minus T3 plus T3 minus T4 plus T4 minus T naught equals to, in the right hand side we get here Q1 by Hi into A plus Q2 into L1 by K1A plus Q3 by L2 by K2 into A plus Q4 by L3 Q4 into L3 by K3 into A, and last plus Q5 by H naught A. So now you tell me the value of heat transfer will be same or not through all the body. Maybe your through first slab, or maybe from environment air to the first slab. Will the heat transfer be same? Yes, it will be same, because whatever the heat, suppose 5 watt of energy or 5 joule of energy is transferred from air to the slab. That means same 5 joule of energy will be carried to the next slab. Same 5 joule of energy will be carried to the third slab, and same 5 joule of energy will be transferred from the third slab to the air. Why? Because you didn't consider any terms of heat loss or any terms of heat accumulation. So that's why I can say that the heat transfer will remain same. That means the value of Q1, Q2, Q3, Q4 and Q5, I can say these all Q values are equal. Means I can say it is Q only. Why? Because there is no heat loss or no heat accumulation. So finally we can say Ti minus T naught equals to Q by HIA plus Q into L1 by K1 into A plus Q into L2 by K2 into A plus Q into L3 by K3 into A plus Q by H dot A. So I can take the common from the right hand side. So you see Q is common and A is common. So if I take the common, then what comes? Q by A within bracket 1 by Hi plus L1 by K1 plus L2 by K2 plus L3 by K3 plus 1 by H naught. So finally Q equals to A into Ty minus T naught within divided by 1 by Hi plus L1 by K1 plus L2 by K2 plus L3 by K3 plus 1 by H naught. So this is the value of heat transfer for composite slab. Now if you remember the heat transfer for single slab, the formula was Q equals to K into A into T1 minus T2 by L. And for composite, yes, here is the formula Q equals to A into Ti minus T naught divided by 1 by Hi plus L1 by K1 plus L2 by K2 plus L3 by K3 plus 1 by H naught. Now, one question arises here. So you see, in conduction mode we had conductivity. Yes, in convection mode we have convective heat transfer coefficient. In radiation mode, we have emissivity. So these terms are there in all modes of heat transfer. Now, if I combine this, if I combine conduction and convection, or if you combine conduction, convection and radiation. So if I combine the modes of heat transfer, there also you need one, heat transfer coefficient. Now what you will take? Yes, so for this we take here overall heat transfer coefficient, and the nomenclature is U. The nomenclature is U. So what is this U? U is called as overall heat transfer coefficient. And why it is needed? Because now you have been taking the combination of the heat transfer. So here you can see amount of heat transfer through composite slab including convection and heat transfer. So already is done. So overall heat transfer, it's coming Q equals to U into A into delta T. Means delta T is the temperature difference, A is the area, and U is called as overall heat transfer coefficient. So now if you try to relate this overall heat transfer along with the heat transfer of composite geometry, so I can find out the overall heat transfer coefficient of composite slab. Now you see, why did I need this? Because in slab the formula was Q equals to K into A T1 minus T2 by L. But when you come to the composite slab, then you don't have only K value. You are including H values also. So here you don't have only single coefficient. You have multiple coefficient. That's why you need overall heat transfer coefficient. So because of this concept, we are adding, or we are summing this overall heat transfer concept. So from here, Ti minus T naught we can cancel, A also we can cancel. So finally we get the value of overall heat transfer coefficient U equals to 1 divided by 1 by Hi plus L1 by K1 plus L2 by K2 plus L3 by K3 plus 1 by H naught. So this is the formula of overall heat transfer coefficient. Okay, so before I end this class, again let's revise this today's class. So today only we discussed about amount of heat transfer through slab, amount of heat transfer through composite slab. In our previous classes we had a formula of amount of heat transfer through single slab, but today we discussed on composite slab, and the formula of heat transfer through composite slab including air inside and outside, it comes Q equals to A into T1 minus T2 by 1 by H1 1 by Hi plus L1 by K1 plus L2 by K2 plus L3 by K3 plus 1 by H naught. Okay, and we get the formula of overall heat transfer coefficient U equals to 1 divided by 1 by Hi plus L1 by K1 plus L2 by K2 plus L3 by K3 plus 1 by H naught. Okay, thank you.